number systems, right? So what are number systems? Number systems, just a second. Number systems are a way of representing data using numbers and symbols. So we have 4 number systems, and those 4 number systems are the binary number system, the octal number system, the decimal number system, and the hexadecimal number system, right? So we've been using the decimal number system for as long as we can remember, right? As humans, we've been using the decimal number system. So I'd like to take you back to primary school level where we learned about something called base values. So base values are positions basically. We have units, tens, hundreds, thousands, and it can go on to 10,000, 100,000, etc., etc. But do you guys remember base values? Does anyone remember base values from primary? If you don't, it's perfectly fine. So imagine that you have boxes, right? You have different boxes. Imagine these as boxes. In the first position, we have a box that can carry 1 toy. In the second position, we have boxes that can carry 10 toys. In the third position, we have boxes that can carry 100 toys. And in the fourth position, we have boxes, a box that can carry 1,000 toys, right? Now, imagine that we had a lot of these boxes, right? A lot of these boxes, and we were to put them in different rows, right? Obviously, suppose that these boxes were all one color, right? If I wanted you to come and fetch me a box that has 1 toy, I'd have to tell you where I had the box that has 1 toy. So the reason we cannot put place values together is because of their different capacities, right? They carry different number of toys, so they have to be positioned. You understand? So we have these boxes. I'm limiting it to 4 for now, but you need to know that it can go on, right? It doesn't have to be limited to 4. So now I have 1 toy here, I have 10 toys here, I have 100 toys here, and I have 1,000 toys here. And now imagine this in a room where the room has 4 rows, right? There's 4 rows. So there's a row with boxes that have 1s. There's a row with boxes that have 10 toys in them, and there's a row with with boxes that have 100 toys in them, and another row with boxes that have 1,000 toys in them. So if I wanted to, okay, so now let's say you have to represent, we have to send someone to come and get the toys, right? We are sending someone from the west, and that person is coming to our warehouse where we store our boxes to collect the boxes, right? So let's say I want to tell this person that I want you to get for me 3,275 toys, right? I want you to give me to go fetch me 3,275 toys, right? And remember, all these boxes are the same color. So I can't tell this person that go and fetch me three red boxes or 2 green boxes. All of these boxes are the same color, right? So the only way we are separating their capacity is through positions. So if I'm going to tell them that I need 3 boxes from the last row, because I have 4 rows, right? 3 boxes from the last row, 2 boxes from the second row, 7 boxes from the third row, from the second row, and because this is the last row, the third row, the second row, and I need 5 boxes from the first row, right? So this is basically how we would represent the number 3275 in decimals, right? We typically represent it using this format. But now, we were allowed to write the number 3275. Why were we allowed to do that? We were allowed to do that because we have something called these digits. So it comes from 0 to 9. The reason decimals are called decimals is because they have 10 numerals that we use when we are counting, right? We use the number systems to represent data. What kind of data? Quantitative data, right? So we use it to say I can count from 1 up until a certain point, right? But for us to be able to count, we need to have a certain number of symbols that we can represent. So that we can use to represent our data. And those symbols are from 0 to 9. So we basically have 10 symbols that we use in decimals. And those 10 symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right? So we're using base 10 because we have 10 symbols, right? But now, the question is, what bases am I talking about, right? What if I told you that there's a way you could represent these numbers but exponential, right? What if I told you there's a way we could name our rows by exponential, right? So what do we name our rows? Exponential. We'll name our rows 10 to the power 0, 10 to the power 1, 10 to the power 2, and 10 to the power 3. So in this manner, we've named our rows exponential. As you guys can see, 10 to the power 0 is 1, right? Etc. etc. So in this manner, we've now named our rows in terms of exponents, right? Because remember, we have these different rows, but instead of me telling the person I'm selling to come get the toys, that I need 3 toys from row 4, I'm going to tell them that I need 3 toys from this row, which is 10 to the power 3. You get that part. Is everyone following? Okay, that's good. So we'll then move to a new number system called the binary number system. So the binary number system is a way of representing quantitative data using only 2 numerals, and those numerals are zeros and ones, right? So we use zeros and ones to represent our quantitative data. So our quantitative data would be the toys that we've been speaking about. So once again, this time the capacities are changing because of the bases. So let's start by saying in decimals we were using base 10 because we had 10 numerals that we could use, 10 symbols that we could use to represent our numbers. So you can count from 0 to 9, but from 10 going onwards, you are repeating those 10 digits. It's now 1 and 0, 1 and 1, 1 and 2, right? You are now repeating the 10 decimals that you already had, right? So now we are given a new number system, and it's called binary. So this number system only has zeros and ones, right? It only has zeros and ones. Why does it have that? Why does it have only zeros and ones? It has only zeros and ones because it is used by electronics. And since it is used by electronics, electronics have only one main resource, and that main resource that they have is electricity. And a way of us saying there is electricity is by representing electricity by 1. And if there isn't any, we write 0, right? So the question to be asked is Bernoulli in a sense. We ask if something is there or not, right? It's either something is there or it's not there. So we then represent it with 1 if it's there, and we represent it with 0 if it's not there. So it's a thing of saying, does the electronic device or does the computer have electricity? If yes, it uses 1 to represent that. If no, it uses 0. So it has that thing, because you can't say I have 1.4 electricity running through me, or I have a certain number of electricity. You can't make it quantitative, right? It's not finite. You understand that part. So with us humans, this thing of saying why do we use base 10 was around this thing of us having 10 fingers, right? With us having 10 fingers, we decided to use the system that has 10 numerals, okay? So again, we're gonna have boxes, but this time the boxes are gonna have a different capacity from the first boxes, right? From the boxes of the decimals, but they're following the same set of rules, right? They're following the same set of rules. Okay, so again, we're gonna have a box that carries only 1 toy, right? Let me start it here. We're gonna have place values. Our place values are gonna be 1, 2, 4, 8, 16, 32, right? When you take a look at this, we have 1, 10, 100, and 1,000. The second place value is 10 times greater than the first one, right? The third place value is 100 times greater than the first one, right? So what they did here was, after obtaining the first one, they multiplied by 10, multiplied by 10, multiplied by 10. Why were they multiplying by 10? They are multiplying by the number of digits that were allowed to have, right? And for decimals, we're allowed to have 10 digits because it's from 0 to 9, right? Then this side, we're only allowed to have 2 bases, so we multiply by the number of bases that we're allowed to have, and so we move from 1, 2, 4, 8, 16, 32, right? But again, what if I told you that there's a way that we could use to represent our place values or to name our rows, right? So we could use exponents, and we would write 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5, right? So once again, we have a box that has 1 toy, a box that has 2 toys. That I want you to go and fetch me 15 toys, right? I want this person to go and fetch me 15 toys. But now, we don't have a box that carries 15 toys, right? We do not have a box that carries 15 toys. How does that person then take 15 toys? We didn't have a box that carried 3,275 toys, but we could take different boxes and they all add up to 15. So 15 is very, very easy to represent. First, you take a look at here, and the rule simply says you look for a place value, the first place value to be greater than the number you're trying to represent. You are looking for the first place value to be greater than the number you're trying to represent. So I'm looking for the first place value that is greater than the number of toys that I'm asked to come and get, right? So I was asked to come and get 15 toys. And when I'm looking here, the first place value should be greater than 15 toys is 16, right? Because 16 is greater than 15. So we draw a line just before we reach there. Why am I drawing a line? I'm drawing a line to say I will not meet the place values to the left of, I will not meet the place values greater than the number that I'm trying to represent, right? I then ask myself, okay, is 16 divisible by 8? Yes. And the answer is yes. So I write 1 because remember, like electricity, it's either something is there or it's not there. So I write 1 if it's there or if it's possible for that to happen, and I write 0 if it's not, right? So it is possible for me to divide 15 by 8. So I'm writing 1, right? If something is possible, I'm writing 1. If it's not possible, I'm writing 0. Base. So after I divide 15 by 8, after I take away 8 from 15, how much am I left with? I'm left with 7, right? I then ask myself, is 7 divisible by 4? Yes. When I write 1, I don't care how many times you get that part. I don't care how many times. The only thing I care about is if it's possible, right? Is it possible for me to subtract or for me to divide that certain number by this value, right? So yes, it's possible. So after I take away 4 from 7, how much am I left with? I'm left with 3, right? So, is 3 divisible by 2?
Yes.
Yes. So, I write 1. And what am I left with? And is 1 divisible by 1? Yes. So, I write 7 because it's yes. So, 4 ones represent 15 decimals. You get that? We were representing 15 toys. So if I had sent the person would come back with 4 different boxes, right? But overall, the boxes would have 15 toys. You get that part? Right. So, but then I have 2 questions, because some of you guys are coming late. Then when you come late, you tend to have problems understanding what we're doing. Because now I'm talking about toys you don't know. But there's also a video, so we'll be fine. Let's try representing a different number now. Let's try representing a different number, right? So let's try representing the number 36, right? So let's try representing the number 36. So after this we have 64, which is 2 to the power 6, and we have positive box and 36. So once you are here, you want to represent the number 36. What's the general rule? The general rule says you look for the first place value that is greater than the number you're trying to represent, right? Oh, another thing here, they can add zeros this side, right? Because all of those, they can add zeros here, right? But those zeros simply means that it can't happen. You already understand that part, right? So if you are doing a question and on the multiple choice you see zeros in front of your answer, it's still the same answer, right? Yes. So we're trying to represent the number 36 in binary. Okay, so what's the first thing we do? The first thing we do is write our place values. So we've written our place values up until 64. And then the rule says you look for the first place value that is greater than the number you're trying to represent. So I'm trying to represent 36, right? as I'm trying to represent 36, what's the first place value that is greater than 36? 64. So I draw the line here. Let me remove this. I draw the line here. Why am I drawing the line? I'm drawing the line to indicate that all the things to the left of this are what? Are greater than the number I'm trying to represent, so I won't move them. There's something I want you to notice. When I started writing my place values, I started on the right hand side and I went this side. So most of you guys make the mistake and start with 2 to the 0 on the margin of your exercise book and go this side, which leads to your binary number being swapped the other way around. It's being reversed, right? So ensure that you start on the right hand side as well. You write. The rule says you look for the first place value that is greater than the number you're trying to represent. So I'm trying to represent 36, right? As I'm trying to represent 36, what's the first place value that is greater than 36? 64. So I draw the line here. Let me remove this. I draw the line here. Why am I drawing the line? I'm drawing the line to indicate that all the things to the left of this are what? Are greater than the number I'm trying to represent, so I won't move them. There's something I want you to notice. When I started writing my place values, I started on the right hand side and I went this side. So most of you guys make the mistake and start with 2 to the 0 on the margin of your exercise book and go this side, which leads to your binary number being swapped the other way around. It's being reversed, right? So ensure that you start on the right hand side as well and you write towards the side. Okay? Right. So once you represent the number 36, we look for the first place value to be greater than 36 and we draw a line. And then we come here. We then ask ourselves, is 36 divisible by 32? Can 32 go into 36? And the answer is yes. Yes. As long as it's, the answer will always be yes if you follow it. The first one will always be yes if you follow the rule of saying the first thing to be greater than correctly, right? So yes, because I can divide 36 by 32, right? So the answer is yes. I don't care for now how many times. It's not about how many times. It's about can I, right? Can I? I don't want to use the word subtract because you guys have this thing of subtracting in your head. This thing of subtracting only works if you are dealing with small numbers. Once you have a lot of numbers, it's not a matter of subtracting, right? So once you have this, then how much is the remainder? The remainder is 4, right? So the remainder is 4. Then you ask yourself, is 4 divisible by 16? No. Okay, the question is there a 16 in 4? No. So I'm going to write C, right? The trick here is to master this thing of the general law. If you have the general law wrong, you get everything incorrect. Because suppose that you wanted to represent 36, but you started here and you ask yourself, is 36 divisible by 8? You find it yes, and many times, and you are not allowed to write how many times something is divisible, because we are only allowed to use 0 and 1. So you then say, it goes into 36 4 times, something which is not allowed, right? You're only allowed to use 0s and 1s. So after, I still have the 4, right? Because I said 4 is not divisible by 16, right? Are you guys following? So I then ask myself, is 4 divisible by 8? No. Since it's no, I put I put 0, right? And then I go on to, it's 4 divisible by 4? Yes. So I'm going to put 1. Is there a remainder? No. So it's basically 0. You then ask yourself that, is 0 divisible by 2? No. Is 0 divisible by 1? No, because it's now zeros. So 100,100 is equivalent to 36 in binary, right? So when you guys try to represent 8 in binary, quickly try to represent 8, then let's take it from there and see. Quickly please try to represent 8.
8.
Yes. Yes. So 8 is simply this it's simply this in binary. How do you obtain it? How we obtained it was rule number 1, look for the place value that is greater than the first place value to be greater than the number you're trying to represent. So I'm trying to represent 8. The first place value to be greater than 8 is 16. So I draw my line there to indicate that I will not be needing the place values to the left of 8, right? Then after that, I ask myself, is 8 divisible by 8? And the answer is yes. So if it's yes, I write 1. The remainder is 0, of course, right? So then there is a 0 over, right? If the remainder is 0, you write 0 until the end. You get that? Yes. If it's not 0, you carry it to the next one and ask yourself if that number is divisible by 4 or by 2 or by 1, right? So good. If you guys are following, I think you guys can already represent the numbers like this. So that's pretty simple. If you follow these steps, then you'll be good because you already understand when we get zeros and you already understand when we get ones. We get ones if there's a yes, and we get zeros if there's a no. So let's move on to vice versa, right? We're moving on to when we are given binary numbers and we're going to decimals, right? You already understand when we get ones. We get ones if there's a yes, and we get zeros if there's a no. So let's move on to vice versa, right? We're moving on to when we are given binary numbers and we're going to decimals, right? So it's very, very simple. Suppose I'm given, let's take 36 because we already know it's binary value, right? We're given 1, 0, 0, 1, 0, 0. We're given this number, right? And we're told that convert this number to decimals, right? If I'm converting this number to decimals, what do I do? The first thing that I do is I write the place values. Are you guys following me? I write the place values. 2 to the, there's nothing that has changed. Instead of me writing 1, 2, 4, 8, I'm writing it exponential. You guys are still following. So I have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5, right? Then once I'm here, I multiply the corresponding positions or indexes, if I might say. So I'm going to have 2 to the 5 times 1 times this one. You guys follow it. I multiply this like this, and then I add. So it's going to be this, we multiply plus this, right? You get it? You guys get it? So I'm going to have plus here, 2 to the 4 times 0 plus 2 to the 3 times 0 plus 2 to the 2 times 1 plus 2 to the 1 times 0 plus 2 to the 0 times 0, right? And this will give me 36 decimals. And this will give me 36 decimal. So note that I've used a notation, and that notation is that 10. That 10 is a subscript of 36. 36 is not an exponent of 10, but 10 is a subscript of 36. Pay careful attention to the fact that 36 is to the left of 10, right? So since 36 is to the left of 10, 10 is a subscript of 36. And 36 is not the exponent of 10. You see that? You see that? I need you to say you see it. Do you see it?
Yes.
10 is a subscript of 36, right? 10 is a subscript of 36. It's like having this thing, right? Yes. So 10 is a subscript of 36. To simply say this 36 is in what? Is in decimals, right? If it was in binary, I would have had 2. I would have had 2 there. If it was in octal, I would have had 8. Hexadecimal 16. You guys get it? So you guys know how to convert from this backwards. Did you guys see how it's done? Did you guys see how we move from binary to hexadecimal? Yes. So it's that simple, really. I should give you guys a task of your own. So let me pick something real quick that you guys can do, so I can see that you are following. Okay. So there are some, we'll practice with the practical 4 questions, right? You practice with practical 4 questions. So convert 1, 0, convert this to decimals, right? Convert this to decimals. That's basically it. So you now know how to write decimals to binary and from binary to decimals. So let's go to the next number system, which is then the octal. We've learned the decimal number system. You know it from primary, you learned it, you understand it. We've now talked about the binary number system. So we're now going to move into the octal number system, right? So with the octal number system, it's the same as the decimal one, but we're now only allowed to use from 0 to what? To 7. We're now only allowed to use from 0 to 7. We're only allowed to use 8 symbols, which are from 0 to 7. It's 8 numerals, right? And so, once again, that's in the head of it, right? The first thing that we do is what? What's the first thing that we do when we want to represent? What do we do? The given a question says, write 16 decimals in octal. What's the first thing that you do? you write your place values, right? So our place values are written as follows: 8 to the power 0, 8 to the power 1, 8 to the power 2, 8 to the power 3. Usually in Octal you don't need to go very much to like 8 to the power 5, like in binary, right? Because this one just escalates that quickly. So we have 1 and we have 8. We have what here? Please check. We have 64 and 525, right? You see, now it has huge gaps, it has huge jumps compared to the binary one, right? So we want to represent the number 16. What does the rule say? The rule says you look for the first place value to be greater than the number we're trying to represent. We're trying to represent 16, which place value is greater than 16. So we draw a line there. After drawing a line there, what do? We then ask ourselves, is 16 divisible by 8, right? This time, we are allowed to say how many times, right? Before, we were not allowed to say how many times because we couldn't say how many times since we only had zeros and ones. Even if there was a remainder, we'd still write 1, right? But here, I can say how many times it goes into 16 because I can use a number from 0 to 7. You get it? So here, it's 16 divided by 8, which is 2, and I'm allowed to write 2, right? Because I'm allowed to write from 0 to 7. You get it? Yes, then the remainder is 0. So it's equals to you get it now. It's this simple. It's literally this simple. It's the same thing. Once you understand the place values for binary, you have now grasped this whole thing, right? You do now understand this whole thing. You can understand the entire thing. All the number systems are simply repetition of one another, right? Just different bases. You get it? Okay, so try representing try representing 177. Try to represent 177 decimals. Try representing 177 decimals in Octal. Please, I'll give you time to do that very quickly, and then you see if you have gotten the hang of it. Because you are trying to understand where these things are coming from. Yes. So when we do the thing of toys. So now, what's happening? We have toys. Suppose I got a tank to distribute, to supply crashes or whatever with toys, right? So now I have different boxes to store the toys. Instead of me just putting all the toys in one place, I needed a way to know how many toys I had. And for me to know how many toys I had to divide the toys into different boxes, right? So I have a box that can carry 1 toy, and I have a box that can carry 2 toys, a box that can carry 4 toys, a box that can carry 8 toys, a box that can carry 16 toys, right? But let's start in decimals. It's better if you start in decimals to understand it. So I have a box that carries 1 toy, a box that carries 10 toys, a box that carries 100 toys, a box box that carries 1,000 toys, let's remove this one. This one carries 100,000 toys, but let's keep it to this one, right? So I have these 4 different boxes, and these boxes carry different toys. The first one is carrying 1, the second one is carrying 10, the third one is carrying 100, and the fourth one is carrying 1,000. What is telling me how many toys must I put in each box? Yini engitshelayo ukuthi manje kumele kulandele 10 toys. Yini engitshelayo ukuthi manje kumele lilandele libe no-100 toys. Yini engitshelayo ukuthi manje kumele lilandele lapho kumele libe no-1,000 toys. Into engitshelayo ilento yokuthi kunalento ebizwa ngo-base 10, right? Lento ebizwa ngo-base 10 ithi thina as humans, when we are counting, we are only allowed to use 10 numerals. And those 10 numerals are from 0 to 9. So if ubala usebenzisa a number from 0 to 9, most of the 10 usuphinda u1 no0 11 yabo usuphinda lezi number yabo, but overall the numbers that we are using is 0 to 9, right? So 0 to 9 is 10 numbers, right? So this thing of 10 numbers is the one that guides me to say the first one is always going to be 1, right? The first box is always going to have 1 toy. And then for me to decide how many toys the second box is going to have, I have to multiply by the number of numerals or symbols that I'm allowed to use, right? So since I'm only allowed to use 10, I'm going to multiply by 10, right? So I'm going to have 1 times 10, right? 10 times 10, and I'm going to have 100 times 10, which will give me. So that is how I know how many toys I must put in each of the boxes, right? Now, suppose that these boxes of mine, these boxes that are carrying different toys, are the same color. So basically they're all white boxes. And there is no way for me to know that this box has 1,000 toys in there and this box has 1 toy in it, right? Because the toys are different sizes, right? So if the toys are different sizes, a big box can have 1 big toy, right? So I need to know that since all my boxes are white, how can I know that this one has 1,000 toys in them, this one has 10 toys in them, and this one has 1 toy in them? And a way for us to know that is by placing them at different positions, right? So we have this position, this position, this position, and this position, right? You see that we now have different positions. So we write our positions from the right to the left. And then what if I told you that there's a way we could represent this in terms of exponents? And the way I could do that is by writing 10 to the 0, because any number raised to 0 is 1, 10 to the 1, 10 to the 2, 10 to the 3. Why am I using 10 to the exponent of something for me to represent this number? Why not any other number? And the answer to that question again is because of the number of symbols you are allowed to have at 10 of them. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is 10 numerals, right? So I'm only allowed to use these 10 numerals to represent my numbers. So that is how we managed to get the scheme of bases. So now I can erase this one. So that's how we were able to get the scheme of bases, right? That's how we were able to get this this thing. We then said, if I were to send someone, say, as a supplier of these toys, suppose I'm busy that day and I ask one of my friends to go and deliver the toys to the crash for me, and I say, I'm required to deliver 1,795 toys, right? I would have to tell my friend, Obuti, you need to take one box from the box that has 1,000, right? And one box, and 9 boxes from the boxes that have 100, right? And I said 1,900 and what? Say 35. You have to take 3 from the ones that have 10, and you have to take 5 from the ones that have 1s. So imagine it like this. Each and every position is a box, it's a single box, right? But in my warehouse, I have a lot of these boxes, right? In my warehouse, I have a lot of these boxes that are stacked, but I cannot stack them together because they have different capacities, right? So a way of me stacking them is to say, I'm going to stack them perhaps to the right, to the left, at the back, at the front, right? So they're divided like that. But instead of me saying, I have one at row 1, I have toys at row 1, at row 2, at row 3, and at row 4, right? I'm going to call these rows 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3, etc., etc. So the number of toys I can have can continue to grow. I can have a box that has 1,000 toys in it, and I can have another one that has 100,000 toys in it, right? So it can grow by this factor of 10, right? You get that part. So if I wanted them to go fetch me 1,935 toys, they would take one box that has this, 9 boxes that have this, etc., etc. So that's how we got into this thing of what? Of bases. So this is how we typically represent 1,910 and 35 decimals, right? This is how we've been doing it over here. We then said, what if we were not given 10 numerals to play with? So I need to understand that the number of numerals we're allowed to play with can change. So for us as humans, we're given 10 numerals, which is from 0 to 9, right? But for computers only use from 0 to 1, right? Computers only use from 0 to 1. So since computers only use from 0 to 1, their first box has what? Their first box has 1 choice always, right? Because everyone, all the phone number systems, the first box always has to have 1, right? And then the numbers we're allowed to use is, right? Because everyone, all the phone number systems, the first box always has to have 1, right? And then the numbers we're allowed to use is from 0 to what? To 1, right? And since our first box has 1, so how do I know how many toys my second box is supposed to carry? I know that by how many numbers I'm allowed to use in that particular number system. In the decimal number system, I was allowed to use 10 numbers. So I multiplied by 10 to get to the next one, right? But in binary number system, I'm only allowed to use 2 numerals. Since I'm only allowed to use 2 numerals, I have to multiply by 2 to move to the next number system. Not the next number system, so to the next place value, right? So to know how many toys might be in my second box, I multiply by 2 and I get 2, right? to know how many must be. The next one, I multiply this one by 2 and I get 4. And then the 8 you're asking about, and then 16. Get this part now. Yes. So that is how we got to 16. And then we were then asked to say, if I wanted to represent a certain number in decimals and represent it in binary, meaning instead of me using the entire decimal system to like use numbers from 0 to 9, I use zeros and ones instead, right? I use binary digits. So for me to use binary digits to represent this thing, I have to then apply the rules that I've been talking about, which is the first one, to search for the number that is the first place value that is greater than the number you're trying to represent. So suppose that I'm trying to represent 36. I'll write my place values. Suppose that I want to represent 36, right? If I want to represent 36, I have to write my place values. I have to write my place values until I reach the number that is greater than 36, right? So from here, multiplied by 2, it's 32, and then 64, right? So these are all my boxes and their toys, right? Then, for me to represent 36, I have to ask myself, which number, which place value, which place value is greater than 36? And I'm looking for the first place value to be greater than 36, right? What is the first place value to be greater than 36? It's 64, right? So I'm going to draw a line there at 64. I'm drawing the line to indicate that I do not need the numbers or the place values to the left of the 36 that I'm trying to represent. I then ask myself, is it possible to divide 36 by 32? And the answer is yes. If the answer is yes, then I'm writing 1. If the answer is no, then I'm writing 0. So after I divide 36 by 32, what am I left with? I'm left with 4, right? So I then ask myself, from this 4 that's remaining, is it possible for me to divide 4 by 16? Is it possible for me to divide 4 by 16? Can 4 be divided by 16? No. So I write 0. And then, is it possible for me to divide 4 by 18 and get a whole number? And get a whole number? Is it possible? No. So I'm going to write 0. Is it possible for me to divide 4 by 4 and get a whole number? Yes. So I'm going to write 1. And then there's 0, right? Then once 0 is the remainder, you write 0 until you reach the end of the place value. So that is how we do it. This is how we do it, right? So you will now understand how we represented 36 decimals in binary is equals to this thing. Right? That's how you represent. And if you want to go back, you then have to take the corresponding ones, the corresponding place values, and do what? And multiply them by these corresponding numbers. As we've been explaining, right? You get that pattern. Great. So you guys you were doing the octal, right? Okay. You're doing this and you will finish what you were writing? Did you finish what you were writing? I gave you a number to represent. I gave you 177 decimals that I want you guys to represent an octal. Did you get it? Toleba. Let me see. So you guys have already gotten the hang of us moving from. We've already gotten the hang of us being only allowed to use zeros and ones for binary, and being allowed to use from 0 to 9 for decimals, and being allowed to use from 0 to 7 for octal. Now, for hexadecimal, we are allowed to use for octal. Now, for hexadecimal, we are allowed to use from 0 to 9. And when you've now reached 9, instead of us saying 1 0 to say 10, like we did in decimals, we now use letters to represent those, right? So we now have a letter to represent 10, 11, 12, up until 15. And those letters are A up until F, right? From A up until F. So today I discovered that when we're dealing with IP addresses, the IP address can be written in hexadecimal, and that hexadecimal can be in small letters. So I thought perhaps we could use capital letters only, but apparently you can use a small letter A, but I don't recommend it, right? Keep on using the capital letters. So we just use from 0 to 9 and from A to F. So A is equals to 10, B is equals to 11, C is equals to 12, D is equals to 18, E is equals to 14, and F is equals to 15, right? We're then going to move from this to representing it. So it's then simple. Have you guys taken this down? I hope so. You guys have taken this down, right? So now, we're going to have, we write from the right hand side, 16 to the power 0, 16 to the power 1, 16 to the power 2, 16 to the power 3, right? We have different place values as usual. So we're going to have 1, we're going to have 16, what's the second one? 256. I think this is 4096. Yes. So these are now our place values. So represent 3,000 decimals in hexadecimal, right? Let's just try it. So the rule says you look for the first place value to be greater than the number I'm trying to represent, right? The first place value to be greater than the number I'm trying to represent is 4,096, right? So I draw a line there to state that I will not be reading the numbers to the left of what? Of 3,000. I might as well put 0k. Then after that, I ask myself, can 3,000 be divided by 256? Yes. How many times? 11 times. So we cannot write 11 because we're not allowed to write 11. But we're allowed to write the letter instead of 11. Which letter we're allowed to write instead of 11? J. So we're going to have B here. Remainder what? So to find the remainder, so it's the remainder R is equals to the initial amount that we have minus the number that we used to divide, which is the place value, times the answer. right? So, what is our I? Our I is 3,000. We initially had 3,000 that we divided by. We divided 3,000 by what? 256, the base value, and we got what as an answer? 11. So what do we get here? 184. So this is your remainder now. Pay careful attention to the mathematics that we use. This is now your remainder, right?
Yes.
Yes. So you carry your remainder. You carry your remainder here. Then once you carry your remainder, you then ask yourself, is 184 divisible by 16?
Yes.
Yes. How many times? 11 times. So we have B again. So to find the remainder, we're going to substitute into the very same formula. We previously had 184, right? Minus 16 the base value times 11 the answer, right? You guys follow it? And what do you get? 8. Right? So you then carry it to the side. And you then ask yourself if 8 is divisible by 1. And you get that it is how many times? 8 times. You are allowed to write 8, so just write it as 10. So BB8 is equivalent to 3,000 decimals. You guys saw how the letters came to play, right? Same rules, everything is the same. So if you are then given AN like this, you are given AN and you are asked to represent it in decimals, right? It's very simple. You have 16 to the 0 and 16 to the 1, right? You have 16 to the 0 and 16 to the 1. You guys follow it? So it's gonna be 16 to the 1 times 11 because A represents 11, right? It represents 10, sorry, times 10 plus what? Plus 16 to the 0 times 15, which will give you, it's 10 plus. So this is how you represent 175. This is 175 decimals. This is 8 in hexadecimal, right? So we know how to convert to hexadecimal and to a part. So that was the last time we've done all 4 of them. You guys following? Are you guys following? Okay, great. I'm glad we have so much time. But the class will be a class here, great. So the question might ask you, they might tell you a story about aliens, right? They might tell you that on Mars, the aliens have 20 fingers, right? And they're saying, guess which base they are using. If the aliens have 20 fingers, then they are using base 20, because as humans we have 10 fingers and we're using base 10, right? You get it? Then they will ask you perhaps how many fingers they have on each hand. If they have 20 fingers, then they have 10 on each hand, right? You get it? Yes. It's as simple as that. And then I think you shouldn't have a problem representing this, right? So that's it. But I'm not saying they're gonna say 20 specifically. Any number, they can give you any number. They could say 100. You know they're using base 100, then they have 50 on each hand, right? Yes. So let's move on to ask what is asking. So asking is the American standard the American Standard of Information Interchange. So we are basically interchanging information between different species, if I'm just saying, right? So as you mentioned, when we are reading, that's a keyboard. If you are pressing something on the keyboard, you're pressing the letter A on the keyboard. The computer doesn't receive it as the letter A, but it interprets it as the letter 65, the number 65, which it then converts to binary, right? After it's 65 decimals and then it converts it to binary, right? You can represent 65 decimals in binary, right? We know how to do that. So it then converts this number to, when you're pressing the keyboard, instead of writing A, it doesn't write A, it writes the number 65. And then the number 65 is converted to what? To binary. So that the machine can understand it, right? Because the machine can only understand binary. Yes, is everyone following? So then we then have a different ways of representing it. So A is equals to 65. Please note that this is capital letter A, right? A is equals to 65. B is equals to 66. C is equals to 67, right? D 68, etc., right? You get this part. And small letter A is equals to 97, B 98, C 99, D 100, right? Then we're gonna have the space. I think it's 31. The space is the space that's 32, if I'm not mistaken. So then we have space which is 32. That's it. So I think these are the ones that you have to know, right? These are the ones that you have to know. You can move from this to anything. If you are, besides, of course, underscores and whatever, right? They're not going to use underscores on the test. They're not supposed to memorize the entire table, right? If you know this and if you know this, it should be fine. If you know this and space, right? And I think there's a 33 for this, 33 for this, and we have what else? Yeah, but this is it. This is it, basically. You have to understand this part. So, the A that you see as is not the same A as that one in what? Hexadecimal. Yes. This A in us is equals to 65 decimals. Right? Yes. So I hope you get that part. I hope you get that part. So as soon as you understand that part, you need to know this for tomorrow's test, right? If you know this for tomorrow's test, you'll be fine. I can't say I assure you, but you'll be fine. I saw something saying if you were to press A, B, C, it's a string, right? A single letter is a character, and multiple ones are a string. You get that? So it would be written as if you were to press this into the laptop, it would be 65, 66, 67, and then split it to its corresponding binary digits in what? Hexadecimal. Yes. This A in us is equals to 65 decimals. Right? Yes. So I hope you get that part. I hope you get that part. So as soon as you understand that part, you need to know this for tomorrow's test, right? If you know this for tomorrow's test, You'll be fine. I can't say I'll show you, but you'll be fine. I saw something saying if you were to press A, B, C, it's a string, right? A single letter is a character, and multiple ones are a string. You get that? So it would be written as if you were to press this into the laptop, it would be 65, 66, 67, and then split it to its corresponding binary digits, right? Any questions so far? No questions. Yeah. So the ASCII one was allowed to carry up until 110. Okay, pressed somewhere, I don't know where. 128 binary codes, right? But then now they've extended it using a Unicode extension, right? So after they extended it, it now goes to 210, 255, right? So they've included the Unicode extension so that we could be able to include things like emojis, right? Because previously, when you look at the keyboard doesn't have emojis or anything, right? So it's not that essential. But when you consider the keyboard on your cell phone, it does include the Unicode extension because it does have emojis, right? And then, of course, emojis are made out of pixels. What are pixels? They are rectangular grid cells, right? Yes, they are rectangular grid cells. But I don't think that's examinable. Right? So I think that's it. Pictures are made out of pixels. Videos are also made out of pixels, and just a series of pictures that are moving really quickly, right? It's like when we used to draw different things on an exercise book, and then we do like this, it looks like perhaps whatever I drawn is moving, you know? So that's basically it. I don't think there's much to it anymore. Does anyone have a question? This is basically us. There's nothing deeper to ask on this one. Oh, then let's talk about 8 bits. What are bits? Bits are binary digits. Bits are binary digits, right? So these are bits, right? These are bits. So here we have 7 bits, right? So there we have 7 bits. So 8 bits is equal to 1 byte, right? Then 1024 bytes is equal to 1 kilobyte. 1024 kilobytes is equal to 1 megabyte. 1024 megabytes is equal to 1 gigabyte, and 1024 gigabytes is equal to 1 terabyte. You guys get it? Yes. Okay, you guys said you've already written a test on random access memory. It's flashing everything equal with the device you're using switches off, and the information was stored in RAM, in random access memory. The memory is lost, right? The information is lost unless you have it written on on non-hexadecimal, right? So that's 8. That is 8. I think it's the end of the session, unless you guys have question, which is the fact that one thing can mean many things, right? Homophones, basically. Right? It's basically homophones. I don't have an example, but girls use them all the time. I don't have an example of something that's ambiguous that I could say in a natural language. But programming languages, precise natural languages have ambiguity, right? So you're gonna need to know that. And then it's a thing of syntax, that the syntax is different, you know what I mean? So the syntax is very different, but then we then talk about the syntax of programming languages when we are now doing Python, right? For now, you guys have done in programming languages, right? Yes. So the only difference that matters this code is that of ambiguity. So that's the thing.